Every single day, it rises in the east and sets in the west, and most of us barely give it a second thought. It's just there, a bright disk in the sky, sometimes hidden behind clouds, sometimes blinding enough that we're told never to look directly at it. But here's the thing, that ball of light is not just a feature of our sky. It is the single most important object in our entire existence. Every photon of light reaching your eyes right now, every calorie of energy in the food you ate today, every drop of liquid water on this planet, all of it traces back to one source, the sun. I'm going to take you on a journey through our closest star, how it was born, what's actually happening inside it right now, how it holds together an entire solar system of planets, moons, and debris, what it has meant to human civilization since we first looked up at the sky, and, eventually, how its story and ours will come to an end. This is the sun. Let's get into it. Let's start with some perspective. Our galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars. The sun is just one of them. It's not the biggest. It's not the brightest. It's not particularly unusual in any way that would make it stand out in a cosmic crowd photo. Astronomers classify it as a G-type main sequence star, often nicknamed a yellow dwarf, though that nickname is a bit misleading since the sun actually emits white light. It only appears yellow to us because of how Earth's atmosphere scatters shorter wavelengths. In terms of size, the sun has a diameter of about 1.4 million kilometers. To put that into perspective, you could fit roughly 1.3 million Earths inside its volume. It accounts for about 99.86% of the total mass of the entire solar system. Everything else, Jupiter, Saturn, every planet, moon, asteroid, and comet, makes up less than 0.2% of the total mass orbiting it. And yet, on a galactic scale, it's unremarkable. There are stars hundreds of times more massive and stars so large that if you replace the sun with them, their surface would extend past the orbit of Jupiter. The sun is, in cosmic terms, a fairly average, middle-aged, stable star, which, as we'll see, is exactly why it was able to support the kind of slow, patient chemistry that life requires. About 4.6 billion years ago, our sun didn't exist. In its place was a vast cold cloud of gas and dust drifting through space, what astronomers call a molecular cloud. These structures are common throughout galaxies, and they are, in a very real sense, stellar nurseries. Something disturbed that cloud. It might have been the shock wave from a nearby supernova, or simply gravity acting on a region that was slightly denser than its surroundings. Whatever the trigger, a pocket of that cloud began to collapse in on itself. As gravity pulled more and more material inward, the cloud flattened into a spinning disk, with the bulk of the material concentrating at the center. As that central mass grew denser, it grew hotter. Eventually, the pressure and temperature at the core crossed a critical threshold, and hydrogen atoms began fusing into helium. A star ignited. This was the birth of the sun, and the leftover material in that swirling disk, the dust, ice, and rock that didn't fall into the newborn star, is exactly what went on to form the planets, including, eventually, Earth. In a very direct sense, We are made from the same cosmic raw material as our star. We are, quite literally, siblings of the Sun. So what's actually happening inside the Sun right now as you watch this? At its core, where temperatures reach around 15 million degrees Celsius and pressures are immense, hydrogen nuclei are being fused together to form helium through a process called nuclear fusion. Specifically, this happens through what's known as the proton-proton chain reaction. 4 hydrogen nuclei combine through several intermediate steps to form one helium nucleus. But here's the remarkable part. The resulting helium nucleus has very slightly less mass than the 4 hydrogen nuclei that created it. That missing mass doesn't just disappear. It's converted directly into energy, following Einstein's famous equation, E equals mc squared. Every second, the Sun converts around 600 million tons of hydrogen into helium. The energy released is almost incomprehensible, equivalent to detonating billions of nuclear bombs every single second for billions of years. But that energy doesn't just zip straight out into space. The photons created in the core have to fight their way out through the dense layers of the Sun above them, bouncing from particle to particle in a process that can take, by some estimates, tens of thousands to over 100,000 years. The light warming your skin today began its journey before modern humans had even developed written language. The Sun isn't a solid object. There's no surface you could stand on, no rocky ground beneath a golden shell. It's a sphere of plasma, the 4th state of matter, organized into distinct layers, each with its own characteristics. At the very center is the core, where fusion happens. Moving outward, energy passes through the radiative zone, where photons slowly diffuse outward over those tens of thousands of years we just discussed. Beyond that is the convective zone, where hot plasma physically rises and falls in churning currents, not unlike water boiling in a pot, carrying energy the rest of the way to the surface. What we perceive as the Sun's visible surface is called the photosphere, a layer roughly 400 kilometers thick, with a temperature of about 5,500 degrees Celsius. This is the boundary that defines the Sun's apparent edge in any photograph. Above that lies the atmosphere of the Sun, made up of the chromosphere, and, further out, the corona, the Sun's outer crown, which is, strangely, hundreds of times hotter than the surface beneath it, for reasons scientists are still working to fully understand. The corona is normally invisible to us, washed out by the brightness of the photosphere, except during a total solar eclipse, when the moon blocks the bright disk and reveals the ghostly white halo surrounding it. Within and around these layers, dramatic events take place. Sunspots, cooler and darker regions caused by intense magnetic activity, solar flares, sudden and powerful bursts of radiation, and coronal mass ejections, enormous eruptions of charged particles flung out into space, which can, when aimed at Earth, trigger geomagnetic storms and spectacular auroras. The Sun's influence extends far beyond its own visible surface. Its gravity is the invisible hand that holds the entire solar system together, keeping Mercury locked in its tight, scorching orbit and keeping distant Pluto more than 5.9 billion kilometers away, tethered to the same system, completing one orbit roughly every 248 years. Without the Sun's mass and gravitational pull, there would be no orbits at all, just planets drifting independently through the void of interstellar space. Every elliptical path traced by every planet, moon, and asteroid in our solar system is a direct consequence of the Sun's gravitational dominance. But its influence isn't just gravitational. The Sun also generates what's known as the solar wind, a continuous stream of charged particles flowing outward in every direction. This solar wind carves out a vast protective bubble around our entire solar system called the heliosphere, which shields the planets to a significant degree from harmful cosmic radiation originating outside our system. And of course, closer to home, the Sun is the engine of life on Earth. Through photosynthesis, plants capture solar energy and convert it into the chemical energy that powers nearly every food chain on the planet. The Sun drives our weather systems, our ocean currents, and the very water cycle that fills our rivers and rains down on our fields. Remove the Sun, and within a matter of days, Earth would become a frozen, lifeless rock. Long before we understood nuclear fusion or stellar physics, humans understood on an instinctive level that the Sun mattered. Across nearly every civilization in history, the Sun was deified, worshipped, and placed at the center of religious and cultural life. In ancient Egypt, Ra was the sun god, believed to sail across the sky each day in a divine barge. In Mesoamerica, the Aztecs believed the sun, Huitzilopochtli, required nourishment to keep rising, a belief that shaped some of their most significant religious practices. In Japan, Amaterasu, the sun goddess, was considered the divine ancestor of the imperial line. The Inca Empire centered its entire religious and political structure around Inti, the sun god, with the emperor regarded as his living descendant. Beyond religion, ancient civilizations built extraordinary structures to track the sun's movements. Stonehenge in England is aligned with the solstices. The pyramids of Giza show a precise relationship to solar and cardinal alignments. Chichen Itza in Mexico was engineered so that twice a year, the setting sun casts a shadow resembling a serpent descending its main pyramid. Even our calendars, our concept of a day, our agricultural cycles, and our earliest navigation methods were all built around observing the sun's predictable patterns. Long before we had telescopes, our ancestors were already, in their own way, astronomers of the sun. The sun, like every star, has a finite lifespan. It's currently around 4.6 billion years old, sitting comfortably in the middle of what's called its main sequence phase, the long, stable period during which it fuses hydrogen into helium at a steady rate. Scientists estimate it has roughly another 5 billion years left in this stable phase. But eventually, the hydrogen fuel in its core will run low. When that happens, the core will contract and heat further, while the outer layers expand dramatically. The sun will swell into what's known as a red giant, potentially expanding so much that it engulfs Mercury, Venus, and possibly even Earth itself. After that, having fused its way through helium as well, the sun will shed its outer layers entirely, creating a brief, beautiful structure called a planetary nebula, an expanding shell of glowing gas. What remains at the center will be the exposed core, an incredibly dense, slowly cooling object called a white dwarf, roughly the size of Earth, but containing the residual mass of the sun itself. It's a strange thing, knowing the ending of our star's story so far in advance, but it also puts our present moment into perspective. We exist in the long, stable middle chapter of the sun's life, the very chapter that made it possible for a planet to cool, for oceans to form, and for life, against the staggering odds of the universe, to emerge and eventually look up and wonder what that bright light in the sky actually was. The sun is not just a backdrop to our lives. It is the reason we have lives at all. It gave birth to the very atoms that built this planet. It powers nearly every process that sustains us, and it has shaped human culture, religion, and science since the very first humans looked up and felt its warmth on their skin. The next time you see a sunrise, take a moment to remember what you're actually looking at. A 4.6 billion-year-old nuclear furnace, 150 million kilometers away, quietly making your entire existence possible. If you enjoyed this journey through our closest star, consider subscribing to Cosmic Journeys for more explorations of the cosmos we call home. Thanks for watching, and I'll see you in the next one.